The second approach is to use the inverse theorem. Right? So I'll just call that the indirect approach. Indirect approach is to use the inverse theorem, which was our formula. F inverse prime at a number, I'm just going to use the number we have here, I'm going to use 1. 1 in this case is 1 over the original function's derivative at f inverse of 1. Okay? So we do not actually need to, this is why I'm calling indirect, we do not actually need to find the inverse function at all. Right? We bypass it, we use the original function's derivative, but there is this small difficulty here. I need to get f inverse of 1, and I do not have the inverse function to work with. I know we computed it over here, but my point is, if you're using this approach solely, then you will not have the inverse function to plug 1 into to get this, in a sense, mystery value that we need to plug into the derivative of f. Okay. Either way, we first need the derivative of f, so we'll go with that. F prime of x is the derivative of this, which is a quotient rule again. So we'll have the bottom times the derivative of the top, which is just 3, minus top, 3x plus 5, times the derivative of the bottom. The derivative of the bottom is just 4. And that gives us bottom squared as denominator. 4x minus 1 squared. Okay, being very careful again. 4x times 3 is 12x, minus 3x times 4 is 0. So the variable vanishes again in the original function's derivative. And we have negative 3 minus 20. Oh, that's ironic. Okay. So simplifying this, we'll have, actually I'm just going to rewrite this with the symbols here. F prime x will be negative 23 over 4x minus 1 squared. Okay, the two are different though, right? We had the derivative of the inverse being negative 23 on 4x minus 3 squared. So it is different, even though the numerator was the same. Right? Nevertheless, we now need that mystery value. We must find f inverse of 1. We've got to find that to be able to plug that into the newly found derivative here, and then we take the reciprocal and we'll have our answer for the inverse function's derivative of 1. Right? So to find f inverse of 1, that would mean it equals some x value. But if the inverse of a function at 1 is x, then equivalently, the original function at this value, the one we don't know, must be 1 itself, right? Because again, inverse functions just switch up the role of x and y, right? If this is an input to the inverse function, and this is its output, that means this is an input to the original function, and 1 would be its output. Right? So we can solve this equation. Right? So what is that equation? It's the original function here, right, equal to 1. So we have 3x plus 5 on 4x minus 1 equal to 1, and find x. All right, so multiplying both sides by 4x minus 1 and solving, we'll have 3x plus 5 equals 4x minus 1. Simply switching some pieces here. I'll subtract 3x, I'll add 1, and we arrive at 6 equals x. All right, 6. 6 is x. So therefore, that means 6 is f inverse at 1. Got it. If 6 is f inverse at 1, that's the number I need to plug into f prime. So f prime at f inverse of 1 is f prime at 6, but f prime at 6 is negative 23 over 4 times 6 minus 1 quantity squared, which is, we have negative 23 over what? 24 minus 1 is 23, 23 squared. So negative 23, a cancellation here, over 23 squared, means I can cancel the square with this. So we get negative 1 over 23. That is the derivative at f inverse of 1. But we know that from the formula, f inverse prime at 1 is the reciprocal of this, which puts us back at negative 23, which is the exact same answer we got for the direct approach, of course. Okay. So the advantage of the indirect approach is I never have to calculate the inverse function in totality. I merely need to find the f inverse at A. I only need to find the value of the inverse at one particular location. I do not need to find it as a function like I did in the direct approach.